Now I'm going to explain a little bit more about this theorem that the set of solutions of a linear homogeneous differential equation is a vector space. And so this theorem just means that if you have a linear homogeneous differential equation, so it is linear in all the derivatives, it can be an equation of an arbitrary order, not necessarily 1 or 2, but it can be an equation of order, I don't know, 2018. So as long as it is linear in all the derivatives of the unknown function, so the left-hand side is the highest order derivative plus some function of t times the derivative of the unknown function of order n minus 1 plus some function times the derivative of the unknown function times of order n minus 2 and so on up to the unknown function itself, and the right hand side is 0, then it is actually trivial to verify that a linear combination of two solutions of this differential equation is again a solution, right? So which means that the set of solutions is a vector space. So here is an example of what it means for a first order differential equation, right? So for a first order differential equation, the dimension of the vector space is going to be 1. Well, but what is a one-dimensional vector space? Well, if a vector space is one-dimensional, it means that it has a basis consisting of just one vector, and any other vector is going to be a linear combination of the basic vector. But a linear combination of just one vector, well, suppose that this is our basis. So our basis is some specific solution of the differential equation, but then any other solution is going to be some constant times this our specific solution. So for example, this or this or this. So in other words, all solutions are constant multiples of each other. So this is what it means. So these are all solutions. So one of them is going to be the zero solution, of course, and so on, right? So all these solutions, they kind of look alike, but not just look alike, they are exactly constant multiples of each other. So this is what the structure of the vector space of a one-dimensional vector space tells us. So that was a first-order differential equation. So let us look at a second-order differential equation. So the set of solutions of a second-order differential equation is a two-dimensional vector space. It means that if you have one solution and some other solution, then any linear combination of them is going to be again a solution. So if this is a solution, then of course a constant multiple is also going to be a solution. So if this is a solution and this is a solution, then their sum is going to be a solution again. Of course, if these solutions are something, well, less trivial than just a constant, then it's probably not so straightforward to see, to kind of see the linear combination, right? So, but here what we see is that all these functions, they are linear combinations of two specific solutions. Now these linear combinations, it could be something more complicated. So imagine that we're going to have, say, e to the, I don't know, e to the minus x, and let's say another solution is going to be, say, integral from 0 to x of e to the minus t square over 2 dt. It's possible, right? So then again, that's our first solution. this is our second solution, then their sum is also a solution, then 2 times the first is still a solution. This is a solution, I don't know, and overall we have a lot of different solutions. So maybe the easiest kind of scenario when we can really visualize it is when one of the two solutions is a constant, which is possible. So imagine that the first solution is e to the minus x, and the second solution is just 1. Yeah. Or maybe let me do it the opposite. So let me change the first solution to 1, and the second solution to this, what's it called? It's the cumulative probability of the standard normal distribution. Right, so in this case, all constants, they are of course constant multiples of each other. They are going to be different solutions, and then of course our function h, which is here, so this is h, so plus the other solution, which is a constant, again going to be a solution. So in other words, in this case all vertical translations of h are also going to be solutions. So in this case it's probably easier to see that the set, if one of the solutions is a constant, then the set of all solutions, they are obtained from the other solution by vertical translations and by scaling. So we're going to have vertical translations, and we are going to have scaling. So this is scaling. All right, I hope it is clear.